We're going to talk a little bit about the transport layer. What does the transport layer do? Well, the transport layer is right below the application layer, right? In the TCP/IP model. We're focusing on the TCP/IP model with the application layer talking about session and presentation, right? Remember we talked about that on Monday, where we had the all the application sessions, presentation layer parts, all the services, right? Okay. Well, transport, it moves the data from the application layer down to the next layer, which we call the internet layer in the TCP/IP model, or the network layer in the OSI model. All it does is it takes these devices and allows them to communicate. Some of the required protocol properties: it has to be fast, it has to have low overhead, it doesn't require acknowledgments, which means I can just talk, you don't have to respond. Pretty simple. It delivers data as soon as it responds, just forwarding. That's all it does. All right? The TCP/IP model, remember, what does TCP stand for? Transport, control, and protocol. TCP is what? Reliable or unreliable? Huh? Reliable. UDP is unreliable, right? U for unreliable. It's reliable. It acknowledges it. It has that connection oriented. That's what transfer means. Transfer protocol, TCP. I make a connection with Cameron. I'm talking directly to him. He knows it. He responds back to me, and going back and forth. All right. Here's a TCP segment and a UDP segment. What's the difference? Big difference, right? TCP packets are way bigger than a UDP. Exception, the application layer segment can be varied in both, right? Pretty simple. Both are going to have source and destination ports. You're going to have a sequence number in the TCP. What is the sequence number? I'm the first, I'm the second, I'm the third, I'm the fourth, I'm the fifth, right? So you can put them in order. Acknowledgement number, the return. So if you return it back, I know you've gotten that packet. That's all it means. Header length, reserved, and code bits. Okay? There's your 16 bits on here. The TCP window tells you the time to live. The checksum value, has it been altered or changed? Right? The error checking. The priority, is it urgent or is it not? And then you have a 32-bit segment if there's any type of option that you want on that packet. All right? I know I'm already putting Cameron in sleeping over here. Well, the UDP is connectionless, right? So it doesn't have a sequence number. So I can flood you with all these packets. When is that good? What if I have a video streaming, right? Audio streaming. You want to have all these packets come in so that you can at least see what's going on, right? If you're doing a lot of high bandwidth programs, utilities such as streaming of web and audio, that's where you're going to be using UDP protocols. If it's data and you're transferring specific bits at a time, you're going to be using TCP. All right? So transport layer. So if I ask you what are the two types of protocols that are in the transport layer, what would you tell me?
TCP and UDP.
Very good, Cameron. You got 100 today. All right, port addressing. Now, we have different types of addressing. Remember, we have port 110, port 80, port 531, which is Internet Relay Chat, if you didn't know. We had the application data that we talked about on Monday. And then you had the application header, then you have the data, right? That's what we're seeing right here. 110, the application port is 110. So we know it's POP3. What is POP3? It's our post office that's delivering our mail to us. Port 80 is application port. We know it's a web page, right? Application port of 531, it's a chat message. So if you want to see what people are chatting about, search for port 531. That gets very interesting, especially when you're looking at AIM messages going back and forth when I was in high school. That was always fun. You're always buddied with all your high school friends, and then you just start pinging them with to get their IP address, and then start ether reeling at that time, ethereal. But anyway, that's port addressing. You're adding that port that we're talking about on the TCP right here, the source port. All right. Now here's the part of the transport layer that is different. Okay, you have your application layer data, piece 1, 2, and 3, which is your data. UDP only provides the source and destination ports. That's it. Where TCP says, I need the source and destination. How am I going to sequence it? How am I going to get it there? The acknowledgments for those received packets. And how am I going to maintain my flow congestion? So, am I keeping up the same pace in the conversation that Cameron and I were having, right? Here's what you're going to see if you're looking at a TCP segment. You have your source port, destination port, sequence number, acknowledgement number, the length reserved, the flags, the window size, which we talked about, the checksum, the urgent pointer, options, data. We already talked about that, right? What is the three-way handshake? Sequence numbers and acknowledgements and termination of session. This is how we start conveying the sequencing, okay? Remember, after transport, to go up to the application layer, you have that session, right? Session's the next layer in the OSI model. That's what we're talking about here with the termination of the session. First sequence, the sender sends over to the receiver. Says, I'm sending you 1,500 bytes. He says, okay, I received it. Sequence number 1501, I'm sending 1501. This actually should have been 1 to 1,500. Okay, so they've got both of them. I'm now sending an acknowledgement back of 3001. That means I'm ready to start at 3001. Does it make sense? Boom, I'm sending 3001. It's lost. But I send 4,501. They get 4,501. Acknowledgement number 3001. Window size 1,500. That means I only got one of those two packets. Sends it back. So I know that I've got to resend these two sequences. Now you're wondering why it's 1,500, right? I talked a little bit about the MTU size, which is, when we're back here, your data part itself can only be 1,500 bits. Make sense? All right. Managing TCP sessions. It's simple. When I'm sending it, it can bounce to many different locations and finally terminate at the endpoint, right? There's no guarantee every packet's going to go the exact same route. So when it gets there, TCP reorders those segments. So instead of segment 1, 2, 6, 5, 4, and 3 getting there in that order, it'll actually segment it and come out and say 1, 2, 3, 4, 5, 6, right? That's what TCP does. UDP, you would see 1, 2, 6, 5, 4, 3. Does that really do you any good? Not necessarily. So which is better? TCP, right? You want someone on the phone that actually understands English and talks to you in a correct sentence instead of saying pig Latin, right? Okay. Acknowledgement of TCP packets. I'm going to start with byte 1. I'm sending 10 bytes. I received 10 bytes. Starting with byte 1. I expect byte number 11 next. That's all it says. And that's how it does. It goes back. It says, okay, I'm starting with 11. Three-way handshake. I'm starting my fin. Brent. He receives it. He sends the acknowledgement that he received it. Then he sends me a fin. I send an acknowledgement I received his fin. That's a three-way handshake. Does it make sense? Now the fun one. UDP. Notice it does not establish a connection before sending data. It floods your network. UDP is one of my least favorite protocols to see on crossing my network. All it is a congestion hog. Hogs up my resources. If you really want to tick off a network administrator, flood it with UDP packets. In other words, stream video. Why do you think network administrators turn off video streaming? Makes sense, right? Again, here you go. We sent 1, 2, 3, 4, 5, 6. Goes around the different routes, comes in 1, 2, 6, 5, 4. Oh, we lost 3, right? Who cares? That's what UDP does. It sends it once. So, if I'm doing bank transactions, which one do I want? TCP. I want to make sure that my data got there and I'm getting the correct data back, right? Because I sure as heck don't want a bank error in the bank's favor. I'll take a bank error in my favor, especially if there's a couple zeros after it, right? Until I have to pay it back. I do not want to do it in UDP. All it does, client 1 sends it to the server, server sends it on there. In this instance, it's a DNS. The client DNS will request be received on port 53. The radius request would be on 1812. Radius is your remote access, your RAS, routing a remote access port. Source port 53, destination port 49152 or 49152. I mean, you can have different sorts and destinations. UDP's well-known port numbers are 1853 and 1812. They will be response on 49152 and 51152. Any questions on the transport layer? It's pretty simple. All you have is TCP and UDP. Again, which one's your favorite now?
TCP.
You have a question? You see if they had a question? No questions? Okay. So we can get rid of that one. Chapter 5. Network fundamentals. We'll talk about the network layer. Now, we've already gone from the application through the session. We created our session with UDP's TCP packets. Now that we have our TCP packets, we're going to come down here, and now we're going to be able to send it to an IP address, right? That's where your internet protocol is going to be. This is where we're going to talk about the internet protocol. All right? And that's how routers connect to each other on this level. So when you hear the term a layer 3 device, how many of you heard a router's layer 3? Layer 3 switch, layer 2 switch. They're referring to the layer of the OSI model they function at. Okay? TCP packet that comes down from the transport layer will come down and flow through the internet layer or the network layer, whichever way you want to call it, depending on whether you're talking about the OSI model or TCP model. An IP is connectionless. There's no established connection with an IP. All right? The best effort is because it's unreliable, there's no overhead for it. It's media independent, it can do what it needs to do. The best effort. IP will not guarantee that all the packets will arrive. Only TCP will. So, IP packet 1 comes out this Ethernet, goes up the serial, goes over the fiber, comes down the Ethernet, gets wireless, gets over to here, right? It can go through any type of medium. Of course, we showed a variety of types of medium there, didn't we? But does it really do you any good to know that? Yes, it does. Because it shows you that it doesn't matter what device that you're trying to put this IP packet through, it'll go through it. All right. Transport layer encapsulation. Remember, when all we had was the application data, or the application header, and the data when we're in the application layer, right? In the TCP layer, we added what we call the segment header. Because when you're at a transport layer, you're dealing in segments. The network layer encapsulates it in a packets. Okay? So all it does is takes this entire protocol data unit, which is a segment, the cluster of data, right? Segment of data. It encapsulates it inside of an IP header, which we now call an IP packet. So when you're searching through Wireshark and you're looking at packets, you're looking right here. So you're looking at what layer? Layer 3. When you're running Wireshark, you're looking at layer 3. That make sense? All right, an IP header. This is what gets added on top of the encapsulated information that we've already talked about. We have the version. We have the IHL. The service type. How long is our packet going to be? Why is that important? Because inside of that carried a specific connection, right? The TCP. We're going to identify it. We're going to have a flag. We're going to have a fragment offset if we need to. The time to live. How many times have you seen that? When you ping something, it has 30 time to lives, or doing a trace route, you have 30 hops that it goes to, right? That's where it sees it. The protocol, we're using IP, a header checksum, means that none of this information has been altered. The source address, a 32-bit address, right? IPv4s are 32-bit addresses. Byte 1 is how many bits? How many bits are in a byte? 8. So if I have 4 bytes, I have... Now you see why it's that long, right? Makes sense? So if I'm taking up this much of that byte, how many do you think I'm taking? A flag is 3. It's a trick question. Source address, and then destination address, and then options. Do I have any options? Remember, options, you can have up to 32 options. However, in TCP, you can only have 30. That's why that extra padding's there. Broadcast domains. What is a broadcast domain? Does anyone know? Going once. Come on, guys.
Is it just the area that the network covers?
Pretty much. Whatever that device is sent to. Okay? Broadcast domain. I have a router. We cover these. A different router could cover this area. Or they could have a router. These could be on a virtual LAN. That could be a broadcast domain. That could be a broadcast domain. All right? This is a broadcast domain. This is a broadcast domain. A router breaks up the broadcast domains. A switch only increases the broadcast domain. All right? If I had a switch here, I would just have one big broadcast domain. Does it make sense? Y'all are following me? A router is the only thing that can break them up. Switches, hubs, bridges, they're all continually adding to. So, how can we increase security in here? If all users have access to here, is this a good way to implement network security? Sure. You're keeping the student records and the private stuff up here while the researchers are down here. Two completely separate networks, both coming out of different firewalls to access the internet, right? IP addressing. A letter from Japan goes to which country? Goes to the US, to which zip code? To which address? Which to street? To which person, right? That's how it gets to us. Post office protocol, right? So the hierarchical addressing on that letter would have been Jane Doe, 170 West Tasman Drive, San Jose, California, 95134, USA. Did we examine, or did we talk about that correctly? Did we say this is how it functions, right? Everyone's with me? Have I lost anyone? Kevin, you okay? All right. We do the same thing, but for each step, it comes down the chain, goes back up the chain of the models. Because when it gets to this router, it's got to rebuild itself. The networking portion and the host portion of an IP address. Now, I know I confused you thoroughly with subnetting, right?
A little bit.
I don't want to get too much into subnetting in here, so if it starts to get to subnetting, I'm skipping it because I'll teach you my way instead of getting into the bits. Essentially, what it's telling you is you have the 32-bit address, and this is a Class C address where you have a 192.168.18 network. Okay? Everything in this octet, the last octet, would be a complete classful address, so 0 to 255, with 255 being the broadcast, 0 being the network, so you'd have 1 to 254 being your hosts. All right? IP routing tables. All it does is know the address of every device on your network. So when I get to the first router, it knows what is connected to the next router. So I've got a 192.168.230. All right? So I want to kick up to here to my 2.1, and I'm trying to send it to, what is it, 3.4? So, hey, I need to find where 3.4 would be. Well, hey, guess what? I've got a router over here that's a friend of mine that's a 3.1. So he's going to call up his friend over here, go through this connection to 3.1. 3.1 says, oh, yeah, I know where 3.4 is. Sends it over here. Think of a router as a zip code. The computer is your house. Your IP address is you. Right? If you're sending something to your cousin in a different zip code, how does it get there? You send it up to your post office, who then says, okay, it's got to go to this zip code. That zip code says, okay, he lives at this house on this street. And when it gets there, then he can pick it up, right? That's all routing does. I just simplified the entire Cisco part to you in about 2 minutes. That's what routing does. It's not a complex, huge issue. It's very simple. It's how you get information from one place to another. Okay? 2.1, send it to 2.2. Well, I've got a network over here that can do it, or I got a network over here that do it, and they both can come over here to here. If I'm going to 10.1.0, what if I'm on the 10.1.1 or the 10.1.2? Which one is it going to go to? It'll forward it to this router. This router will then decide which is the best route to go. All right? So that's what we call the next hop. This router says, oh, my next hop is going to be this interface, which is the 1.2, because it's directly connected to that 10.1.1. The 10.1.1 is where it needs to go on that network. And so that's how it gets there. See, the R's, meaning they were directly connected. C is the direct connect. R's mean that they're the remote routers. They're on the remote router. So in my routing table, I can see for my next hop, these two are there. They have to go out this port or go to this router, and I can connect to that network. Does that make sense? So if I want to send a letter to Yukon, it's got to go through Oklahoma City. So what I would see is 731, my C, I'm directly connected right here out my fast Ethernet to that router. 73110. The schools or the school's address. I'm going to send it out to Yukon. I don't even know what the zip code is out there. Anyone? We'll say Bethany, 73008. All right. So this is 73008. Well, Oklahoma City is 73010. I can see 73008 via 73010. So I know to send it to 73010 so that it can forward it from itself out that direct connect. All right? It's saying that my fast Ethernet is connected via the 192.168.2.2 is directly connected fast Ethernet to the 10.1.2 network and the 10.1.1 network. So that's how it goes. Yeah, it's just the graphical part of it. Dynamic routing protocols. Router A says that it's connected to. It'll say it's connected to directly connected to 2.2, but it's remotely connected to 1.2. This one will say it's directly connected to both this router, and it will be able to see these. So I'll be able to see this from here, at least one hop away. All right. I can configure it manually to go to here, but it sees it automatically from here. So these three routers can share the networks so that when he says, okay, I got to go to 10.1.1.1.0, he knows how to go. Then he goes to go through B, B goes to C, C sends it out. All right. Now we're explaining the routes. We did examine the routes earlier, where we examined, and I brought them up in the packet tracer earlier this semester, so I'm not going to redo that. Is there any questions on that?
Sure.
Everyone awake? Do I need to talk to Bueller? All right. You'll like that, don't you? I am probably the weirdest professor you've ever had. And Kristen's in agreement with me. Was that 4? All right. Yeah, I hear you, Kristen. I have good ears. Cole, she hasn't learned that I'm an umpire. We hear everything that is said on the field. We're not blind. We see everything. But I'm not the umpire that intentionally calls phantom calls so that I can make it up on the other team later on. The only time I ever made a phantom call is because the coach told me to eject him. Because he didn't give me a reason to eject him. He just told me to eject him to fire up his team. That's the only phantom call I've ever made. He didn't spit on me, didn't touch me, didn't say anything derogatory to me. He just said, "Can you eject me so I can fire up my team?" I said, "What?" Well, okay, coach. You're out of here. Anyway. Do what?
You sounded like an ump just then.
I am an umpire. All right, coach. You're out of here. In this chapter, I'm going to explain the structure of IP addressing, demonstrate the ability to convert between an 8-bit binary and the decimal numbers, which you're going to need to know for your wireless problem. Given the IPv4, classify a type and describe how it is used in a network. Explain how addresses are assigned by networks and ISPs. Great. This is the subnetting one, so we're going to go real quickly through this one. Okay, IP address structure. Y'all know what an IP address is, 32 bits long, right, for IPv4. It's broken up into binary bits of 4 octets of each bit, 32 bits long. Each bit is byte, or 8 bits is byte. Converting a decimal to an 8-bit binary. We go down like that. I'm not going to worry about it. I'm going to show you the shorthand way of doing it. Again, I'm going to show you the short way to do it. Broadcast address, host address. Again, I'm going to show you a short way to do it. Classify and define an IPv4. That's subnetting. I'm not going to do that. Classify and define an IPv4 address. Okay, what is an IPv4 address? What are the three types of communication in the network layer? And describe the characteristics of each. Well, you have a unicast, a broadcast, and a multicast. Okay? Unicast transmission means there's one packet that's going on at a time. One transmission can go on that network segment at a time. How good is that? Not reliable. Well, it's very reliable, but it's not resource intensive, but it's not cost effective. Okay? Limited broadcast. That means occasionally I will send out a broadcast to everyone till they say, yes, this is my packet, this is my packet, this is my packet. How bad is that? That's too over intensive, right? Because you're flooding your network all the time with broadcast, sending unnecessary traffic, i.e., you're sending a lot of UDP messages. Multicast transmission. I can send multiple envelopes to different points on my network at the same time if I need to. So that's better use of the resources, right? Still low cost to the overhead. And I'm not going to get into the RFC business, but all that is a request for comments. If you had a request for a comment about the host IP range, you could do a comment on 790. Multicast address is 1700s. Experimental addresses are 173330s. All this is talking about the host addresses. You can go up to from 0000 to 223 network. The 224s to 239s, or the 240 network essentially, is multicast addresses. And then your experimentals or your research facilities are 240 and up. What this means is, here's your A, B, and C, here's your D, and here's your E. Class A, B, C, D, and E. Make sense? Y'all memorizing this from network. Okay. I have 3 private networks. All of them are on a private network. A Class A private network is the 10.0 range. Your Class B is a 172.16 to 172.31.255.255 network. And then your 192.168 network is your Class C private address. It's actually 192 period, and also 127 is reserved for your loopback address. Anything higher than a 224 and up, you won't use. Won't be live. So what happens with NAT is inside this router, it'll be a 192, but externally you'll see that one live IP address that comes in to talk to that on that serial port or that WAN port of that router. That's the only IP address you know to that company or to that network segment. And you can have 10 billion IP addresses behind it and you'll never know it. All right, unless you're the network administrator on it. What is the purpose for the special addresses? Well, a 169 address, you probably have seen that. It says IANA or ARPA. What that means is you do not have connectivity anywhere. The 169.254. It can only communicate with anything that is seeing on the local LAN. That is it. It does not have any external out on your subnet. It can only see what's from that switch in. A router does not forward a 169 address at all. And if you use a 192.0 network, it'll only communicate in the local LAN as well. All right, well, here's how you classify and define them. I'm not going to get into it. Read my Stokely subnetting cheat sheet. Assigning IP addresses or assigning addresses, it comes originally from the IANA to get your public address. They can be assigned in by also your ISP. If they have a bigger cloud, then they give you what they call a public IP address. You will then assign that public IP address to your external port on your router, and you can refer it to a DMZ. Why would you want to do that? So that that public IP address, that you only want to buy 2 of them probably, or 6, no more than 6, depending on how many servers you're going to put out here on your public web. And then you have private on the internal network. All right? Any questions on that? You can assign them via DHCP address, which is Dynamic Host Control Protocol, which means the computer automatically assigns them for you. You don't have to worry about it. It'll assign an IP address, a subnet mask, and default gateway. And you can also add a DNS server, and it can assign that as well if you have a DNS server on your local network. You can assign different subnetworks for the different devices. We can get out to that a little bit later on. Assigning addresses, like we said, is the IANA. They do it for the global. And ARIN does it for the United States. ARIN. All right. So you have 3 tiers of ISPs. You have the Internet Backbone, which is the IANA label. You have Sprint, Cox, all those are going to be your tier 1 level. Then you have tier 2 levels, which is your next gen level, mainly your countries. And then you come down here and then you're on tier 3. So when you create a domain, you're a tier 3 level. Does that make sense? IPv6 is a 64-bit address. I'm sorry, it's a 128-bit address. And there's an example of an IPv6 address. How much harder is it going to be to memorize? This puts 1 million plus IP addresses per square foot on the face of the planet. Just to kind of give you a rough ballpark. Not that we need that many IP addresses, right? I don't think we'll ever run out of live IP addresses for IPv6. Subnet mask. We've talked about that. The network mask. If I'm doing an ANDing, I'm not going to worry about ANDing and ORing. I don't really want to talk about that. Calculating addresses, that's subnetting. I don't want to do that. Testing the network layer. How do you test it? Use pings and trace routes, right? Can you get out? Can you get from here up to the server or to the router and it comes back? All right. Trace route just tells you how to get from this point to this point, how many hops it took. That's all it does. ICMP, Instant Control Message Protocol, or Internet Control Message Protocol. You want to block that because you don't want the ping of death to happen to your network. Is there any questions? I know I skipped over a lot of the subnetting stuff, but read my Stokely cheat sheet, because as we start going in over the after spring break, I'm going to start going in, and when we talk to VLSM, I'm going to really hit into the subnetting area. Okay, the variable length subnet masks, CIDRs. That's when we're going to start getting to those. Up until then, we're going to be using classful addresses. Is everyone okay? Y'all functioning? All right. Now, on Monday, you will receive in the news feed your first riddle. I would highly encourage you to try to figure it out. Once you figure it out, email me, give me a call. I will give you riddle 2. You do that for the first 4. When I give you the 5th one, you have to take the answers from the first 4 to figure out the 5th riddle. The 5th riddle will tell you where it's located. I will also tell you on Monday what all the information I want off of this router. And you will have to bring me all that information. The first person to do so will make an A in my class. I know a couple people are back there drooling, just ready to get that first riddle. Do what? So you can get out of my class?
I don't want to.
You want to?
I don't want to.
Oh, you don't want to get out of my class?
Oh, overboard, aren't they?
Uh-huh. You still get the A for the class. But you can still stay and learn. And I'm not going to tell you, kick you out of the class.
I don't think there'd be much of a point if you already have an A.
Well, make your money's worth. You just won't have to worry about your grade. That's one less grade you have to worry about. But it's still a challenge to go find it anyway.
It is.
Because I know how you and I can work on something else with a tool that we'll be getting in this next week. Yeah, I'm going to make you mad. I bet I can breach it before y'all can. No, I'm talking about an instructor's computer. Oh, he already told me that he thinks you're going to be the first one to get it.
Oh, he knows.
Yeah, I told him that y'all are going to be trying to breach it. He goes, okay, I'll accept the challenge. So he said he's going to leave it unlocked a couple times. Yeah. Just to see if anyone will try it. And he said that you'll be the one that get it.
It's a wrap.
We'll see. All right, any questions?